Now that we've seen that there is an inherent strain placed on cycloalkanes based on both torsional strain and angle strain, we can actually evaluate that strain quantitatively. And there's two ways that we can go about doing so. The first way is simply by looking at the heat of formation, which we call delta HF, 0. And we've talked about heats of formation before when we talked about alkanes. And we see that the delta H formation simply reflects a molecule's relative stability. So relative to typically isomers. Now, cycloalkanes are not isomers of one another, but if you think about it, all the simple cycloalkanes consist of methylene groups in varying numbers. So cyclopropane has 3 methylene groups, cyclobutane has 4 methylene groups, and so on and so forth. So what we can do is we can analyze cycloalkanes stability based on the delta H of formation per methylene group. And keep in mind that the more negative the delta H, the more stable and less strained the ring is. So the more negative the value of delta H formation, the more stable the structure is, and therefore the less strained the ring is. So, but again, we have to compare based on per methylene group. So essentially what we're doing is we find the heat of formation of a molecule and we simply divide that number by the number of methylene groups. And here's a table in your textbook that shows on the left-hand column there you see the measured delta H F value, and then in the next column you see the delta H of formation per methylene group. So we've simply taken the value of delta H of formation, heat of formation, and divided by the number of methylene groups. So cyclopropane has 3. If you take 12.7 divided by 3, you get 4.2, and so on and so forth. Now notice cyclopropane has a positive heat of formation, and therefore it has the most strain that's associated with it. And as you see, as you go larger into the larger and larger rings, the heat of formation becomes more and more negative up until you get to cyclohexane. And then it kind of tapers off a little bit. And then it isn't until you get to cyclododecane that you see a marked uh, increase in the negative value of heat of formation. Again, cyclododecane has 12 carbons, and so it can actually take on that chair conformation as well. It essentially takes on 2 chair conformations and makes it more stable. And everything in between is going to have some torsional strain associated with it because it cannot take on that nice chair conformation. So a couple of things that I want to point out. Recognize that what we're really interested in is the heat of formation per methylene group. This is how we can really compare the structures. So going down, you see that it reaches a point where cyclohexane has the most stable structure. And then as you increase the ring, so as you go from cyclopropane to cyclohexane, the structures are becoming more stable because you can minimize all of the angle and torsional strains. Then as you go larger, that that energy minimization is lessened because there's not that perfect chair conformation until you get into the really larger rings. Also, one thing to keep in mind is that we can compare this value to that of a free methylene chain, a calculated methylene chain that is strain free. So that's what we are comparing, right? And so we see that on the far right hand side, if we simply take into account what the heat of formation, the calculated heat of formation of a strain-free molecule would be, and we take the difference between the actual value and that calculated value, cyclohexane essentially has no strain associated with it, which we've already seen before. So that's the take home. And you also see that cyclopropane has a lot of strain. It has the most strain associated with it, which we would predict due to that high amount of angle strain in the molecule. Not only angle strain, but also torsional strain due to all of the carbon-hydrogen eclipse bond, and that since it's planar, it cannot deviate from that to alleviate some of that strain. The other quantitative evaluation of strain comes in the form of the heat of combustion of cycloalkanes. Now, recall, right, delta H0 of combustion, we abbreviate delta HC, and we know that an organic compound will undergo combustion, right, with oxygen to yield CO2 and water. Now, why is this important to understand? Well, in general chemistry, we learn this reaction. We say, okay, let's say I have octane, C8H18. So octane is going to react with oxygen to give me CO2 and water. And of course, I should know how to balance this reaction. And just to kind of give you a brief review on balancing, we see that you balance the carbons first. So I have 8 CO2s that are going to form. Then I balance the hydrogens. So I need to have 9 water molecules, which leaves me 25 oxygens on the right-hand side, and therefore to have 25 total oxygens on the left, I have to have 25 halves. Now, also remember, heat of combustion is per mole of organic compound, and therefore when I'm looking at the heat of combustion, this is the equation that I'm using. I'm not multiplying everything by 2 because I want to know how much heat's given off per 1 mole of octane. Okay, so that's important to understand. Now, the other thing to understand is that what does that heat of combustion mean? Well, it is the heat given off in the reaction, right? So it is part of the products, but it's given off, and therefore it's an exothermic reaction. It is a negative value. We typically, when we talk about heat of combustions, we talk about a positive value, but in reality, it is a negative value. Okay, so so keep that in mind. It's a negative value, and we'll talk about that in a little bit. The other part that you need to understand is, well, when I'm talking about octane, now I know that octane exists in several isomeric forms. And when I look at the delta H of combustion for all of the isomers, I see that they have different heat of combustion values. For example, when I look at straight octane, I measure the heat of combustion. I see it's 1308 kilocalories per mole. Now, when I go to 2233 tetramethylbutane, I see that the delta H value is 1303 kilocalories per mole. What does this mean? It means that it's giving off less energy, and therefore it is more stable. It's giving off less energy, which means that it is more stable. Why? Well, let's take a look at an energy diagram to see if we can kind of picture what's going on in the process. And we're going to start off as our baseline of the products. Notice that both octane and 2233 tetramethylbutane give the same products. They both yield 8 moles of CO2 and 9 moles of water. And therefore, the end, relative energy is going to be the same for both of them. And so when I start with octane, I see, okay, it's releasing 1308 kilocalories per mole, right? So it's a negative value. It's releasing that amount of energy. And when I compare it to my branched alkane, and I see it's releasing only 1303 kilocalories per mole. So where it started from is a lower energy than that of octane. Do you see that? Where it started from is a lower energy than octane. And molecules that are lower in energy, we say are more stable. And we can measure that energy difference of 5 kilocalories per mole. Now that might not seem like a lot of a very big difference, but in the grand scheme of things, it is a big difference. And as a matter of fact, why would this be important? Well, we use alkanes for fuel, right? So I would rather have octane in my tank than a branched octane, because straight chain octane is going to release more energy. It's less stable, it releases more energy. And when I go from moles to gallons, now that difference in energy becomes vast. And that's real important to us in terms of how much bang for the buck do I actually get. So how does this relate to cycloalkanes? Well, cycloalkanes again are not isomers of one another, so we can't compare directly the heat of combustion of cycloalkanes. But just like we saw with the heat of formation values, we can do the same thing for the heat of combustion values, and we can simply divide the heat of combustion of the cycloalkanes by the number of methylene groups, and then we can compare the heat of combustion per methylene group. And so when you do that, you get, here's a nice little table that kind of shows the various delta H of combustion of all of the cycloalkanes per methylene group. So notice we've divided the delta H of combustion of all these by the number of methylene groups in each ring, right? And again, you see that cyclohexane has the lowest energy, so it is the most stable. And relative to a strain-free methylene chain, you see that there is essentially no difference between the two. So when I look at a table that compares the strain based on the delta H of combustion, I see right away that cyclohexane is the most stable, right? Why? Again, because of that chair conformation that it can undertake, which alleviates all angle strain. It also alleviates all torsional strain. And so our understanding of that distortion is backed up quantitatively by the energy we get for both heat of combustion and heat of formation.